Okay, so for our topic for this week is going to be operational amplifiers. Um, this is what I am going to cover. Again, this is a supplemental lecture. This is not the official material, although a lot of the material that is published in UVLE is contained also here. So this is what I intend to cover. First, I'm going to discuss the circuit model of an operational amplifier, then the characteristics of an ideal operational amplifier. Then we'll go into analyzing operational amplifier circuits. Okay? We're going to take up a lot of examples. So analyzing operational amplifier circuits, I'm going to give a lot of examples this week, rather this Tuesday, today. And then on Thursday, I'm going to add some more examples, progressively becoming more difficult. And then the end, we'll take up the case when we have cascaded operational amplifier circuits. So let's discuss what an operational amplifier is. First of all, we call this opamp for short. Masyadong mahaba yung operational amplifier, so a lot of times we just say opamp. Okay. And this is a very widely used circuit building block, particularly in analog operations. The op-amp is capable of performing basic arithmetic operations. That's why the name is operational amplifier. You're going to find out later on that it is capable of doing multiplication, addition, subtraction. If you have a combination of operational amplifier circuits, subtraction, and the like. In fact, later on, you're going to find that it can even do differentiation and integration. We're going to study op-amps from a purely behavioral standpoint. In other words, we're going to study it like a black box. All we're going to do is specify how the black box behaves when it is inserted in a circuit. So in this particular course, we're not going to be concerned with how op-amps are implemented. In EEE 131, you're going to get a glimpse of what the inside of an op-amp looks like. But for this course, all you need to know is what its circuit model is going to be. Okay. An operational amplifier has 5 terminals, and this is the schematic symbol of your op-amp, with the 5 terminals. Okay, what are your 5 terminals? You have your inverting input, which we designate V minus. You have your non-inverting input, which we designate as V plus. You have your output, V sub O, and then you have 2 power supply connections, 2 power supply voltages. That's V plus and V minus. A lot of times, you will not show the power supply anymore if it's not going to affect the behavior of your op-amp in the circuit in which it is placed. So pag minsan hindi na nyo makikita yung V plus at saka V minus. There's an implied 6th terminal, and that is your ground. So that's not shown here, but it is implied that all of these voltages, V minus, V plus, V sub O, they are all measured with respect to ground. And so are the positive supply voltage and the negative supply voltage. So this is your schematic symbol again. And you designate the inverting input with a minus sign, so this minus sign, and you designate the non-inverting input with a plus sign. This is an example of an operational amplifier. So this is a real-world operational amplifier, the LM741. This operational amplifier is almost as old as I am. In other words, when I was a student, there already was the LM741. It's a general-purpose operational amplifier. So this is what it looks like, what we call the through-hole version. Okay. And this is its pin-out. What do we mean by pin-out? Okay, when we look at the top of the operational amplifier, so this is your operational amplifier. Okay, this is pin 1, pin 2, pin 3, pin 4, and then the other side would be pin 5, pin 6, pin 7, and pin 8. And this is what we call the pin out. It tells you what the pins what particular connections are made by the pins, ano? So for example, in this particular case, itong pin 2 is your inverting input. Okay. Pin 7 on the other side is your sorry, yeah, pin 2 is your inverting input. Um, Pin 3 is your non-inverting input. And then you connect your positive supply at pin 4, that's this pin, and you connect your negative supply at pin 7. By the way, there's a mistake here, no? This should be the one of these should be the negative supply, no? I can't seem to recall which one. Okay, so I'll correct that later, no? For the moment, don't worry about itong pin 1 at saka pin 5, which is your offset null, no? By the way, may I ask, no? Maybe you can raise your hand na lang, no? Has anybody here already seen or used an op amp in an experiment? Has anyone of you? Meron na ba? So meron na, no? So hindi ito something that's very esoteric. Actually, dapat at this point you already would have been exposed to an op amp in one of your labs. So this is another version of the 741. This is what we call the true hole version. You actually use the true hole version usually in experimentation. This is something that you can plug into a prototyping board and then easily wire to other components. This is what we call a surface mount version. So this is how actual electronic products are built using surface mount components. And notice that this is very small. No? It's very small. This is the size of this is a quarter, a US quarter. So it's much smaller than the size of a quarter. And you already know that electronic products now are really very miniature already. They can be implemented or they can be miniaturized. Okay, any questions so far about the operational amplifier? So this is the circuit model of an operational amplifier. This is what describes how an operational amplifier behaves when it is used in an electric circuit. So what is the circuit model? Between the inverting and the non-inverting input, all we have is a resistance. We call it Rin. And then you have a voltage-controlled voltage source in series with an output resistance Rout. And that is what produces your output voltage V sub O. And then here you have your positive supply voltage, and here you have your negative supply voltage. So in essence, the inside of an operational amplifier or the model of an operational amplifier is just a voltage-controlled voltage source. And you already know how to deal with circuits with voltage-controlled voltage sources. A lot of your exercises in nodal analysis, for example, had voltage-controlled voltage sources. So if you plug in this particular model into a circuit containing an op-amp, you should be able to analyze any op-amp circuit. Let me repeat that. No? If you have an op-amp circuit and you plug in this model with the tools that you have already learned, you should be able to analyze any op-amp circuit. Now, what then are we taking op-amps for? No? Well, because when you deal with an ideal op-amp, you're going to see that there are simpler ways of analyzing operational amplifier circuits. So that's what we're going to take up later on. No? Okay, now the input resistance is typically very large. Typically, that is in the meg-ohm range, The output resistance is typically small. Typically, this is less than 200 ohms. 200 ohms is small when compared to mega ohms. The gain So this is a voltage controlled voltage source. So your constant here, AOL, is a gain. It is a voltage gain because your controlling variable is a voltage, your output is a voltage. So this is a voltage gain. The gain, we call this an open loop gain. The reason why we call it open loop gain, later on you're going to learn why. This is typically very large. AOL is typically in the 10,000s, 10 to the 4 or 10,000s. So those are the typical values of the parameters of your op-amp model. Again, your input resistance is very large in the meg ohm. Your output resistance is small, typically small, in the hundreds of ohms. And your open loop gain is very large. This is in the 10,000s. If I apply KVL to this particular loop, applying KVL here, okay, I'm going to get AOLED minus I out R out. So let's assume that there's something connected here. That this is not an open circuit. Let's assume there's something connected here such that a current will flow. So AOL minus I out R out should be equal to V sub O. So that's this equation here. V sub O is AOL ED minus R out I out. Now ED, this ED is actually the voltage from your non-inverting input to your inverting input. So that is V plus minus V minus. And we call that our differential input voltage. So I'm just now describing some terminology when it comes to op-amps. That is called your differential input voltage. Now, the output voltage cannot be indiscriminately large or indiscriminately small. There will be a cap to the maximum value of your output voltage and the minimum value of your output voltage. And usually that cap is dictated by your positive supply voltage and by your negative supply voltage. So your V sub O, this V sub O, will usually fall between two limits, a maximum positive value and a minimum negative value. And those limits, again, are dictated by V plus and V minus. Any question? Any questions so far? So I'm just describing the behavioral model or the circuit model of an operational amplifier. Excuse me. So what do the output characteristics of our operational amplifier look like? Output characteristics, that's a plot of V sub O versus ED. I want to plot V sub O versus ED. So I'm going to neglect, first of all, I'm going to neglect R out. Anyway, sabi nga natin, R out is usually small. So I'll neglect this. Okay. If I neglect R out, so this is going to cancel out. And so my output voltage is just AOLED. So that's what I'm showing here. V sub O is equal to AOLED. And what is that? That is the plot of this line. So if you take a look at this line, this is actually V sub O is equal to AOL multiplied by your differential input voltage. Okay. And then what did I say? I said that the value of V sub O cannot become indiscriminately large. We don't expect this line to continue upward all the way to positive infinity. We don't expect this line also to continue downward all the way to negative infinity. At some point, we say the output saturates. So where does it saturate? The maximum value Vmax, that's positive saturation, and the minimum value Vmin, which is your negative saturation. Okay. When it operates from this point to this point, from this point to this point, we say it is operating in the linear region. It is operating in the linear region. Here, it is in positive saturation. Here, it is in negative saturation. Okay, note that the larger the value of AOL, the steeper this curve is going to be. In other words, okay, if I increase AOL, what will happen to the curve? The curve is going to be like this. Let's say I increase AOL. So this is a larger AOL. In fact, what will happen if AOL is very close to infinity? Anong mangyayari pag yung value ng AOL is very close to infinity? No? Remember what I said earlier? Ang value ng AOL is very large. No? It's in the 10,000s. So when AOL is approaching infinity, what happens? This line is almost or becomes a vertical line. So maybe I can draw that. No, it becomes a vertical line. So itong orange line na to, this orange line, this is when AOL is equal to infinity. And what is the value of E sub D in the case where AOL is equal to infinity? Pag tinignan ko yung value ng E sub D, in this vertical line, what is the value of E sub D? E sub D is just equal to 0. Iisa lang yung value ko ng E sub D in this vertical line, and that is E sub D is equal to 0. Okay, so this is how an op-amp behaves. This is how the output of an op-amp behaves. Okay, so let's take an example. Okay. Let's take an example. This is an open, we call this an open loop op-amp circuit example. So for the circuit shown with the given input voltages, plot V sub O versus T. So I have a circuit here. Ang nakakabit, what is connected to my non-inverting input is a signal. And the shape of that signal is this green curve, V sub S. Okay, so it is a time varying signal. It varies with time. No? So this axis, the horizontal axis, is time. And the shape of my signal is, sometimes we call this a triangular wave. That is this V sub S. And then I have connected to my inverting input a constant voltage, which I call Vref. And this is the value of Vref. That is the value of Vref. Okay, so to one input, to my non-inverting input, I have a time-varying signal. And to my inverting input, I have a constant voltage. What will my output look like? So what did we say was the value? What is this? Sorry, my computer is acting on by itself. No? What did we say was the value of V sub O? V sub O is equal to AOL E sub D. So first, I want to know what E sub D looks like. What is E sub D? E sub D is V plus minus V minus. Yun yung E sub D. So I'm going to subtract from this curve, I'm going to subtract this value. Okay? Imagine yung green curve, babawasan ko ng Vref. What's going to happen is I'm just going to be pushing that curve down. No? If I subtract a constant value from a time signal, then I'm pushing the curve down. So this is going to be my plot for E sub D. And my output voltage is going to be a constant AOL multiplied by this. That is going to be my output voltage. So ano magiging itsura ng output voltage ko? No? If I have a large constant multiplied by this curve, what is my output? My output is just going to be a very, very large triangular wave. No? It will be a very, very large triangular wave. Yun yung magiging value ng output ko. However, we mentioned that, okay, the minimum or the maximum voltage cannot exceed VCC. So this is an assumption. And the minimum voltage cannot be smaller than minus VCC. Okay. So what will happen? Because AOL is very large, konti pa lang increase ng E sub D. So let's say we start with E sub D equal to 0. It is just at a very small value, yung output ko will already be VCC. No? And then a very small negative value, yung output ko will already be minus VCC. Okay, so this is what it's going to look like. No? So notice at this point here, okay, at this point here, my output is already saturated, positive saturation. And at this point here, my output is already negative saturated, negative saturation. So I'm only in the linear region here. No? This is the only place where I am in the linear region. Okay, ano yung linear region? Again, going back to here, this is your linear region. That only happens between these 2 points. Okay. Outside of those 2 points, I am in positive saturation or negative saturation. Now, what will happen if A sub L approaches infinity? If A sub L approaches infinity, okay, this region, this linear region, is going to become much thinner. In fact, it is going to be just a point. And this line is going to be vertical. This is going to be a vertical line. And therefore, what is this circuit? This circuit is actually a comparator. It is a comparator. I have a reference voltage. Okay. When my input signal is less than my reference voltage, my output is negative. No? When my input signal is greater than my reference voltage, my output is positive. So that's how my comparator behaves. I have a simple simulation of this. I just wanted to show it to you. Just give me a few minutes. Okay, I have a very simple simulator here. So this is my triangular wave, okay, and this is my constant voltage. No, my constant voltage in this case is 1 volt. So you can see the 1 volt there. Okay, now my triangular wave, if I take a look at the characteristics of my triangular wave, the minimum value is minus 3 volts, the maximum value is 3 volts, and the period is 1 millisecond. 1 millisecond corresponds to 1 kilohertz. So it's actually a 1 kilohertz triangular wave. And I can take a look at how that looks like. Okay, so you can see now, the purple is my triangular wave, and the green is my DC value. So that's how those two look like. No? Okay, what about this? No, this is not an op-amp yet, because what I did, I adjusted the gain so that the gain is quite small. If you take a look at the gain, no, my gain is 10 volts per volt, or my gain is equal to 10. When in fact, an op-amp, the gain I mentioned is in the 10,000s. Is in 10,000s. So my gain is 10 volts. My minimum output is minus 5, so that is my Vmin. And my maximum output is 5, so that is my Vmax. So what do I want to do? I want to take a look at what this is going to look like. No? So let's take a look at what that looks like. So this is what ends up in the simulation. So you can see that when the purple signal is less than the green signal, okay, more or less, I have a negative output. And when the purple signal is greater than the green signal, I have a positive output. But note that my output still has a certain amount of slope. It still has a certain amount of slope. Now, what will happen if I adjust my op-amp so that it has a more typical gain? Typical gain of my op-amp, let's say, let's make it 10,000. No? So 10,000 is yeah. Just going to, so this is now 1,000. This is 1,000 volts per volt. And I just want to make it equal to 10,000. So I adjusted now my gain. If you take a look, my gain is now 10,000 volts per volt, which is a typical op-amp gain. If I continue now the simulation, take a look at what happens to my output. It's now going to be very steep. Okay, it's going to be very steep because my linear region now has become very, very narrow. So you can see how an op-amp works, no? Counting difference in voltage, between the inverting and non-inverting input will already cause the op-amp to saturate either positive saturation or negative saturation. Very small difference. In fact, if my gain is 10,000, what will it take for my output to reach 10 volts? 0.00001 input will cause my output to already reach 10. That's how sensitive your operational amplifier is. So are there any questions with respect to this? Any questions with respect to this example? I want to hear some voices. Ano, I might have lost you. May tanong ba?
Sir, unrelated po sa pump, ano po yung application na gamit niyo po pang simulate? Mukhang maganda po siyang pang-apply.
Yeah, it's a very simple simulation tool. No? It's called Every Circuit. No, I think there might be a free version, but mine is a purchased version.
Okay po.
It's a nice tool for visualizing. No, pag gusto mo i-visualize kung ano nangyayari, it's a nice tool.
Opo. Thank you po, sir.
Okay. Okay. So let's go on. No. So what is your ideal op-amp? Ano yung ideal op-amp? No? Ang ideal op-amp natin, yung input resistance natin is infinite. Anong ibig sabihin nun? No? The resistance between this point and this point is infinite. In other words, this is an open circuit. No? Parang walang nakakabit dito between the negative and the positive. So that, if that is infinite, ibig sabihin nun, yung I minus, the current entering your inverting input is equal to I plus, the current entering your non-inverting input, which is equal to 0. That is if your input resistance is infinite. And then the second condition for your ideal op-amp, your output resistance is equal to 0. R out is equal to 0. So kung 0 yan, nawawala yung term minus I out, R out. Ano? Ang output voltage ko is just now V sub O is equal to AOL E sub D. This is the output voltage regardless now of the value of I out. And the third condition for your ideal op-amp is that your open loop gain is equal to infinity. Sabi ko kanina, it's in the 10,000s. Pag ideal yung op-amp mo, we just consider it equal to infinity. And if your open loop gain is equal to infinity, your E sub D, no, from this equation, E sub D is V sub O over AOL. Since AOL is infinite, E sub D will be equal to 0. Or V plus will be equal to V minus. So ito yung pinakita ko kanina doon sa output characteristic curve na pag infinite na yung AOL natin, our linear region becomes a vertical line. Naalala nyo doon sa curve kanina? Yung linear region natin becomes a vertical line, and in that vertical line, E of D is equal to 0. Now, ang kagandahan sa op-amp, if we make use of these assumptions, or if we assume that the op-amp is ideal, nagiging madaling-madali ang analysis ng op-amp circuits. The analysis of your op-amp circuit becomes very, very easy. Of course, you can analyze it using the model, no? Yung model na binanggit ko kanina. But if you make this ideal op-amp assumptions, it becomes very easy to analyze your circuit. And the nice thing about it is you lose very little precision. Very little loss in precision. As a matter of fact, when you assume that an op-amp is ideal, your error is oftentimes even less than 1%. Yung nagiging error mo is even less than 1%. Okay, so these conditions translate into two constraints. No? So the first constraint, we call it the input voltage constraint, because AOL is very large. No? V plus is approximately equal to V minus, and when AOL is equal to infinity, V plus is equal to V minus. Now note that that is only in the linear region. V plus is equal to V minus. And we say that a virtual short exists between the inverting and non-inverting input. So pag ito yung op-amp mo, okay? If this is in the linear region, we say that there is a virtual short, no? Which makes V plus equal to V minus. Now, why do we say it's a virtual short? In fact, this is a little bit of an enigma. It's a virtual short because it is not a real short in the sense that your current is equal to 0. No? Because since Rin is equal to infinity, your current is equal to 0. Now we know that in a short circuit, your current is not usually 0. Diba? In fact, when you short circuit two terminals, usually you have a significant current flowing between those two. So that's why you call it a virtual short. It's a short with respect to voltage, but it's actually an open circuit with respect to current. Okay, so having said that, can you tell me what is wrong with the following circuits? Okay, let's start with circuit A. No? Can I call out names? Clyde, anong problema sa circuit A?
Yung current po is not 0.
That's right, no? Circuit A is actually an invalid circuit because your current is not equal to 0. Yung pumapasok sa inverting input or yung lumalabas dun sa non-inverting input will not be equal to 0. Whereas, remember that infinite dapat yung impedance between or resistance between your negative and your positive. So in effect, it's really an invalid circuit. Okay, what about Albert, no? Anong problema sa circuit B? Albert, have we lost you?
No, sir.
Nakapaghabol ka na ba? What's the problem with circuit B?
Sir, try lang. Siguro po yung input voltages po are not equal.
That's right, no? Sa circuit B, there's supposed to be a virtual short between your negative and positive, and therefore dapat equal yung V minus at saka V plus. Pero dito, ang V minus is 10 volts, ang V plus is equal to 5 volts. Okay? So this is worst case, if you try to connect these voltages to an op-amp, ang worst case na mangyayari, masusunog yung op-amp mo, no? Ito rin, no? If you try to connect this circuit to an op-amp, ang worst case na mangyayari, masisira yung op-amp mo, no? But then if your op-amp does not get destroyed dito sa letter B, it will just not be operating in the linear region. Kasi yung condition for a virtual short is if it is operating in the linear region. In other words, it could be operating in positive or negative saturation. If I go back to, let me go back to this curve, no? So this is your linear region, ito. Okay, dito lang valid yung virtual short. If it is not operating in the linear region, it is operating either somewhere here or somewhere here, no? And here or here, your ED can be any value, right? So in that particular example, yung ED natin would be 10 volts minus 5 volts, no? So that can be anywhere here, right? Or if it's negative, it can be anywhere here. Okay? 5 volts pala minus 10 volts, sorry. Okay, negative feedback. So anong nakita nating problema dun sa example na binigay ko for an op-amp, no, operating in open loop mode, no? So what example was that? Again, this example, ano? What was the problem here in this particular example? Okay, ang problem was ang liit, there's a very, very small input voltage range or ED range where your input is in the linear region. As a matter of fact, if it's an ideal op-amp, this linear region is actually just a point. It's just a point, no? Because this will be a vertical line. So the problem is napakabilis niya mag-saturate. That is the problem, no? Now, how do we prevent it from saturating? We employ what is called negative feedback. Ano yung negative feedback, no? A part of the output is fed back to the inverting input of the op-amp. Okay? Part of the output is fed back to the inverting input of the op-amp. Now, what does that do? The feedback causes E sub D to decrease as V sub O increases. So isipin na lang ninyo, no? Tumataas yung V sub O, part of that ay feedback to the inverting input. Ang mangyayari, yung inverting input, kasi tumataas yung V sub O, bababa yung E sub D. Pag bumaba yung E sub D, bababa din yung V sub O. No? That's what you call negative feedback. So it tends now to regulate itself. V sub O tends to regulate itself because of the feedback, na hindi siya magiging masyadong malaki o hindi siya magiging masyadong maliit. So another way of saying this is V sub O is trying to prevent itself by feeding back part of it to the inverting input. It is trying to prevent itself from saturating immediately. And the op-amp now becomes what we call a closed loop circuit. When you have feedback, you call that closed loop. When you don't have any feedback, you call that open loop. So that's the reason why A sub L, we call that the open loop gain, because that is the gain of your amplifier if there is no feedback. That is the open loop gain. When there is feedback, your gain value changes. So negative feedback is very important if you're going to implement a linear operational amplifier circuit, a linear circuit. So linear circuits are circuits where the output is linearly related to your inputs. Pag yung relationship between output and input is linear, and it doesn't have to be a straight line linear, no? It can be a linear differential equation. Then you call that a linear circuit. And Ano yung mga examples ng linear circuit chip? Amplifiers, buffers, adders, filters. In general, filters are linear circuits. So how now do we analyze op-amp circuits? Paano natin ngayon i-analyze yung mga op-amp circuits? So sabi ko, if you make the assumption that the op-amp is ideal, it becomes very easy to analyze an op-amp circuit. In fact, this is a personal experience of mine. No? I'd encounter students na medyo upper class students na, and then when you talk to them about op-amps, they don't seem to be able to grasp how to analyze op-amp circuits properly. And in fact, these students are usually very intimidated when they see op-amps. But the truth of the matter is, if you just understand these very few simple rules, it's actually very easy to implement or to analyze op-amp circuits. What are these rules? No? First, you always check first that there is negative feedback. Ano? Check that there is negative feedback. Kasi kung walang negative feedback, then chances are your output is either positive saturated or negative saturated. Then second, you apply the golden rules for ideal op-amps operating in the linear region. And those golden rules are just the two rules that I told you earlier. V plus is equal to V minus, okay? And then I plus equal to I minus equal to 0. Okay? Then third, you use nodal analysis. Just use nodal analysis. No? I should have added a fourth rule here. No? I should have added a fourth rule. Let me do that. 4, check for saturation. Check for saturation. So those are the 4 simple rules for analyzing op-amp circuits. So let's take examples. I'm going to start now with the many examples that I have. The first example that I have, and this is a standard circuit. So this is a standard op-amp circuit. We call this an inverting amplifier. I'm sure some of you that have already had some exposure to op-amps in high school, for example, or in the lab, alam na alam ko ano yung magiging output nito in terms of its input. So, okay, what is the problem? We're going to derive the relationship between the input and the output for this inverting amplifier. So derive an expression for the output voltage in terms of the input voltage and the circuit resistances. Assume the op-amp is ideal. Okay, una-una check. Is there negative feedback? Meron bang negative feedback? Team C, is there negative feedback?
Yes, po, C.
Yeah, it's obvious, ano? Your output is here. So part of that output is sampled through this resistor and fed back to the inverting input. It has to be the inverting input. No? If it feeds back to the non-inverting input, that is positive feedback, that's going to make matters worse. Lalo magsasaturate. No? So yun, there's negative feedback. No? Okay, then we apply the simplifying assumptions for your op-amp, ano? And what is that? No, that the voltage at this point is equal to the voltage at this point. Okay, so V minus is equal to V plus. But what is V plus? Ses, can you tell me what V plus is?
0 po.
That's right, no? V plus is 0 because this input is grounded, no? So V minus, which is equal to V plus, is equal to 0. No? And then third, I just apply nodal analysis. Saan ako mag-apply ng nodal analysis? Where will I apply KCL? I apply KCL, in this case, to the inverting input. Okay. So what are my current components here? This is one current. This is another current, and this is another current. No? This is I minus. Okay. So what is this current? What is this current? That's V minus VI all over R1. No? V minus, again, sorry. That's V minus VI all over R1. That's the first current. No? This current here, itong paakyat, that is plus V minus VO all over R2. And then what is this current? Clyde, ano yung current nito, na ito?
0 po.
That's zero, you know, because that's one of the golden rules of your ideal op-amp, 0. So this should now be equal to 0. But we already said that V minus is equal to 0. So actually, this is 0, and this is also equal to 0. So what do I get? No, I just get minus VI over R1 is equal to VO over R2, or V sub O is negative R2 over R1 V sub I. Okay. Now, why do you call it an inverting amplifier? Inverting amplifier, the gain is negative. Okay? The gain is negative. So whatever the value of the input, no, nagiging negative, of course multiplied by R2 over R1, tapos kukunin mo yung negative nun. So very simple analysis. Was there anything hard about the analysis? Wala, di ba? Very straightforward. I could have analyzed this using the model of the op-amp. No? So I could have plugged in the model, yung merong RI, tapos merong AOLED, tapos merong RO. Then I could have analyzed this using nodal analysis, but and then plugged in the values of RI and RO and AOL. I could have done that, but because I assumed it was ideal, my analysis became very easy. Okay. Here's example 2. So this is now my inverting amplifier. Okay. So same circuit. And I already know that V sub O is equal to minus R2 over R1 times V sub I. So what is my expression for V sub O here? Clyde, can you tell me what is V sub O? Expression for V sub O.
Medyo naliligaw po ata ako, sir.
Gamitin mo lang tong formula to, no?
Okay po.
So what is V sub O?
V sub O po is 4K, negative 4K over 1K times
V sub I, no?
V sub I.
So it's just minus 4 multiplied by V sub I, no? 4K over 1K times V sub I, okay? So Albert, let's fill up this table, ano? Ano magiging value ng V sub O pag yung input natin is 1 volt, Albert?
Negative 4 po.
Negative 4. Sige, tuloy mo. What about 2 volts?
Negative 8 po.
Okay. What
Yes,
about 5 volts?
Negative 20 po.
I will put that here. And then,
Then,
ito,
4 po. 4 volts.
4 volts,
12 volts.
12 volts,
And then 20 volts po.
20 volts. Any comments from anyone? Says, any comments?
Yung limit niya po is 12 volts.
Okay, exactly, no? Exactly. That's what I want you to be careful about, ano? remember what I said, that your output cannot be indiscriminately large or indiscriminately small. May limit siya, no? And usually that limit is dictated by V plus and V minus. So in this particular case, sabi natin V max is equal to V plus and V min is equal to V minus. So ano dapat yung value nito, Albert?
Bali po negative 12 po.
Yes, that's right, no? So actually, mali itong entry for 5 volts and minus 5 volts. Okay. For 5 volts, this should be negative 12 volts. And for negative 5 volts, this should be 12 volts. Okay. So be careful of that, no? Be careful of, kaya nga linagay ko dun sa procedure natin kanina, kaya nga dinagdag ko to, no? You have to check for saturation. Okay. Any question with regard to that? Okay, let's have some other examples, no? This is another standard circuit. This is another standard circuit. We call this your non-inverting amplifier. Okay, so same problem, derive an expression for the output voltage in terms of the input voltage and the circuit resistances. Assume the op-amp is ideal. Okay, so hindi ko pinakita dito yung V plus V minus. So pag hindi pinakita yung V plus V minus, the assumption is you just assume that's not going to affect the output, ano? Okay. So if this is ideal, ang ibig sabihin nito, if this is ideal, if ideal, V plus is equal to V minus. Sorry. V plus is equal to V minus. No? Okay. But what is V plus? What is V plus? In this case, it is VI. It is VI. So kung VI yan, ano yung voltage dito sa point na to? What is the voltage at this point? Assess. What is the voltage at this point?
No?
Yeah, I'm asking, ano? What is?
Narinig ko ba?
Yes, so I can hear you.
VI yun po.
Yeah, that's VI. This is going to be VI. The voltage there is going to be VI. And so now what do we apply? We apply KCL now here. KCL at the inverting input. Okay. So ano yung currents dito? Yung papunta dito, from right to left, that's VI over R1. Okay. Yung current na paakyat dito, what is that? The current up here, that's plus VI minus VO over R2. Tapos yung current na papasok, alam natin zero yan, ano? Because I minus is equal to 0. This is equal now to 0. Okay. By the way, no? Note that dito, there's negative feedback, no? Remember I told you check that there's negative feedback. So note that here there's negative feedback. Nakikita natin yun. Okay, so if I now simplify this, what do I have? I have VI times 1 over R1 plus 1 over R2 is equal to V sub O over R2. No? Or V sub O is just equal to R sub 2 times 1 over R1 plus 1 over R2. Oh, sorry. Ah, yeah, that's right. Times V sub I. No? V sub O is equal to R2 times V sub I. Okay. So what is this? I can simplify this. This is 1 plus R2 over R1 multiplied by V sub I. One plus R2 over R1 multiplied by V sub I. So why is it non-inverting? Your gain is positive. Gain is positive. That's why it's called a non-inverting amplifier. Okay. So if I want, for example, a gain of 2, what do? If I want a gain of 2, I just make R2 and R1 equal. So my V sub O is going to be 2 V sub I. No? Depending on the gain I want, I just adjust R2 and R1. Okay, the limitation of your non-inverting amplifier is the minimum gain is equal to 1. When does that happen? When is the minimum gain equal to 1? Team C, when is the minimum gain equal to 1? Or when is the gain equal to 1? Two possibilities. Can you tell me?
Kapag sir, di po ako sure. Kasi po sir, pag equal yung R2 and R1, twice po yung gain.
Yeah, that's right. Oh.
Pero pag 1 lang sir, hindi ko pa sure yung values ng R2 and R1.
No, make a guess. When will the gain be equal to 1?
Sir, hindi po pwedeng 0 yung R2 and R1.
No, if R2 is equal to 0, di ba?
Apo sir, sorry nga po.
Right? If R2 is equal to 0, in other words, if this is a short circuit, your gain is equal to 1. What's the other condition for your gain being equal to 1? Pag R1 is equal to infinity. What is infinite? Ibig sabihin open circuit. No? So yung gain natin is equal to 1. This is either if R2 is equal to 0 or R1 is equal to infinity. And that's when you get a gain equal to 1. And yun yung pinakamaliit na gain na pwede mong magkaroon. It cannot be smaller than 1. Hindi kagaya nung itong inverting amplifier. If I wanted to have a magnitude of a gain that's less than 1, I can, ano? For example, if I wanted, instead of a multiplier circuit, if I wanted to divide the input, let's say I wanted the output to be half the input, then I'd make R2 1/2 of R1. Pero dito sa inverting amplifier, sa non-inverting amplifier, you cannot do that. The minimum gain is equal to 1. Are there any questions? Okay. Which brings me to my fourth example. So this is a situation, ito yung situation nga na R1 is equal to infinity. No? Itong kanina may sa inverting amplifier may resistor dito connected to ground. Now if I make that equal to infinity or gawin kong open circuit yan, this just becomes what you call a buffer. A buffer. Okay. Another way of looking at this, okay, since I minus is equal to 0, no? Ito yung I minus. There is no voltage drop across R. Okay. In other words, V minus V sub O over R is equal to 0. V minus, the voltage here, minus V of O over R is equal to 0, or V minus is equal to V of O. But remember, ideal op-amp to, but V plus, which is equal to V of I, is V minus. So what do you get? You just get V of O is just equal to V of I. Because V plus is equal to V minus. And that's what you call a buffer. And a buffer is a very important circuit. Siguro iniisip nyo, no? What good is a circuit whose gain is equal to 1? What good is a circuit whose gain is equal to 1? Well, the advantage of having a buffer is it isolates a source from a load. No? The point of the buffer isolates it isolates a source from its load, no? From its load. Let me give you an example. I'll give you an example. No? I don't have space to do that. Let me create a new slide. So, ano yung ibig sabihin ng isolates a source from its load? No? So let's say I have a source. This is a source. Okay. V of S with a Thevenin or a source resistance, or you might think of this as the Thevenin equivalent of a circuit. No? So this is a source resistance R of S. Okay. Let's say I want now to connect a load, and the load resistance is R of L. What will be the voltage across my load? What will be V of L? Can you tell me what it will be, Clyde? Ano yung magiging value ng V of L?
Voltage divider po.
Yes, voltage divider. So what is that? That's
V
V
sub
of S.
times R sub S over R sub S plus R sub L.
Yeah.
I mean R sub L po sa taas pala.
Yeah. Okay. V of S RL over RS plus R of L. No? Kung maliit yung value ng R of L, okay, if R of L is small relative to R of S, V of L will be small. Okay? Anong gagawin ko? Lalagyan ko ng buffer. So lalagyan ko ng buffer. V of S. No? Ito yung R of S. So ano yung buffer ko? My buffer will be let's just call that R, no? This is R of S. Okay, this is now going to be V of L, no? Dito ko ngayon ikakabit yung R of L ko. Okay, ano magiging value ng V of L ko? What is the value of V of L? Okay. Anyone?
V sub S po.
Yes, that's right. No? V of L will be equal to V of S. Right? Bakit? No? Wala kang current na pumapasok dito. No? Wala kang current na pumapasok dito sa V+, and therefore wala kang voltage drop dito sa R of S. And therefore V+ is just equal to V of S. But V+ is equal to V-. So yung voltage dito sa minus will also be equal to V of S. Tapos wala kang current dumadaan dito dahil I minus is equal to 0, and therefore V of L will also be equal to V of S. No? In other words, that's the point of your buffer. No? So in effect, this manages now to isolate the load from the source. Yung voltage ko ngayon across my load, the voltage across my load will be the full value of V of S. Hindi kagaya dito na nung kinabit ko yung load, walang buffer, biglang lumiit yung value ng voltage ng V of S as seen by the load. No? In effect, the portion of V of S that will now be across the load will become very small as opposed to this. So that's the purpose of a buffer. And you see this situation a lot in real life. No? For example, this might have been a sensor. Let's say this is a sensor. Medyo malaki-laki yung value ng Rs of S. So pag kinabit na natin yung sensor dun sa sensing equipment natin, biglang babagsak ngayon yung signal na tinitignan natin. No? Let's say this senses temperature. So halos hindi mo na makikita yung temperature. So ang gagawin mo, lalagyan mo ng buffer. No? Para pag kinabit mo ngayon yung sensor, pag kinabit mo ngayon, makikita nitong load yung buong value ng sensed quantity. Is there any question with regard to that? I hope you can see the value of the buffer. No? Okay, the thing about buffers, so this is your buffer, ang maganda sa buffer is pag tinignan mo yung input resistance. So what is input resistance? No? The input resistance is the resistance looking into the input terminals of your circuit. So this is my circuit. My input terminals are my non-inverting input with respect to ground. No? If I take a look at the input resistance, it is equal to infinity. Because this current, the current flowing here is equal to 0. And therefore, my input resistance is equal to infinity. Samantalang dito, if I take a look at my input resistance, I have a virtual short, a virtual ground here, no? So this is a virtual short. So what resistance do I see? Ang nakikita kong resistance is just equal to R1. That is my input resistance here, no? So from the perspective of input resistance, if I want to preserve my input signal, your non-inverting amplifier is a very nice amplifier. Your inverting amplifier, meron kang konting input resistance. Anyway, that's also what you will base your selection of R1 and R2 on. No? You also select R1 and R2 based on what you want your input resistance to be. Okay. Any questions? Okay, maybe one or two more examples. Maybe we can do this very quickly, and then I'll stop, and then I'll just continue next time. No? So this is again a very trivial example. Okay, V plus is equal to V minus. First of all, note there's negative feedback. Okay, then you have V plus is equal to V minus, no, and therefore, since V plus is equal to 0, you have V minus is equal to 0, no? Because you have a virtual short here. And then if I apply KCL at V minus, okay, I have I in is equal to V minus VO over RF. Okay, but this is equal to 0. So I just get now minus VO over RF. No? Or V of O is just now negative RF times I in. No? So the input current is converted to an output voltage. the input current is converted to an output voltage. Of course, there is negation. Negative lang yung gain. Still, the output voltage is proportional to the input current. And then the last example that I'll take up for today, this is called an inverting summing amplifier. Okay. So again, we see here that first we see that there is negative feedback. No? Part of the output is fed back to the inverting input. There's negative feedback. Okay. Then we also see that V plus is equal to V minus, which is equal to 0 because your V plus is connected to ground. Okay. Then applying KCL at V minus, KCL at this point. Okay, what is my equation going to be? I have V minus V1 over R1. So that's this current, okay, plus V minus V2 over R2 plus V minus V3 over R3 plus V minus VO. So ito naman yung current naman papunta rito over RF is equal to 0. Is equal to 0 because I minus is equal to 0. Okay. So what comes out is V minus multiplied by 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over RF is equal to V sub O multiplied by 1 over RF. Sorry. No, sorry. What am I doing? V minus times sorry, Burano. This is 0. This is 0. This is 0. This is 0 and this is 0. Sorry, I don't know what I was doing. I have minus V1 over R1, okay, minus V2 over R2, minus V3 over R3 is equal to V sub O over R sub F. No? Sorry. Okay. So that is the output, okay, in relation to my inputs. Okay, if I make, no, if R1 is equal to R2 is equal to R3 is equal to RF, what do I get? Ano? I just get V sub O is equal to negative of V1 plus V2 plus V3. That's why you call it an inverting summing amplifier. An inverting summing amplifier. Now, if you wanted it to be a weighted summer, no, if you wanted it to be a weighted summing amplifier, then you would adjust R1 and R2 and R3 according to the weights that you want. For example, if you want R1 to be twice, if you want the weight of V1 to be twice the weight of V2, which correspondingly would be twice the weight of V3, no, then you would make R1 1/2 of R2 and R2 1/2 of R3, no? Something like that. Okay. I'm going to stop there. No, I'm going to stop there. But I think you should already get the gist of the process for analyzing op-amp circuits. What I've been teaching you are all standard circuits. So these are all standard circuits. These are all what you would see in a cookbook, for example, for op-amps. In other words, if you look for a summing amplifier, ito yung makikita nyo. If you look for an inverting amplifier, yung circuit kanina makikita nyo, and so forth and so on. No? So you can actually already practice. I have additional examples here. I'll probably show you the entire slide deck so that you can also work on the other examples during your free time. So you have your non-inverting summing amplifier, you have your difference amplifier. Okay, then I have some other examples. So I'll add that to the material that I'm going to post. Okay, are there any questions? Any questions so far? Okay, remember you have to practice. No, I'm teaching you this. When I teach it to you, it seems, or it might seem to you clear, but you don't know whether you really understand it unless you practice. So you have to practice solving problems. Okay. Okay. So if there are no questions, I'll officially end it here. And for those of you that want to stick around to ask questions, you may. The rest may already leave. Thank you.
Thank you po, sir.
Yeah, you're welcome.
Thank you po.
Thank you, sir.
Okay.